Welcome to KU Pathshala, a novel initiative of the University of Kerala to archive educative videos. CLIF is taking part in this venture wherein we are exposing the instruments being housed in the CLIF campus for the benefit of people who want to use the facility for their research purposes. The facility is managed by qualified technicians, highly trained, as well that governed or managed by faculty who are all experts in the field. The idea behind housing all the instruments under one roof is that not only that you will be able to use the instrument, but also get the feel of how exactly an instrument is functioning. For that matter, we are encouraging people to come to CLIF while their samples are analyzed so that they will be able to understand how the instrument is functioning to get the desired results. We have qualified faculty as well as outside experts who will be speaking during the video filming on the application value of each instrument being housed in this. The central instrumentation facility, which is being housed in the Kariavattom campus, has got about 21 equipments, high-end equipments, being supported by different organizations in the country. I'm not going to the details of the functioning of the instrument as is going to be demonstrated in the videos. So I welcome you to view the videos, and straight away we see the videos about the functioning of the instruments which are housed in the CLIF campus. Thank you very much.
Hello, my name is Dr. Vinesh Vijay. I am a faculty in Indian Institute of Science Education and Research, Thiruvananthapuram, or otherwise called ISER TVM. I have around 20 years experience working with different aspects of NMR spectroscopy, and have been doing research for the last 15 years in NMR spectroscopy. Nuclear magnetic resonance spectroscopy is probably the most important technique for obtaining structural information of organic molecules. I am going to give you a brief introduction about NMR and the kind of information that you can retrieve from NMR experiments that can be done in the 400 MHz NMR facility in Kerala University at Kariavattom campus. The principle of NMR is based on the fact that certain nuclei with odd atomic mass or atomic number such as 1H, 13C, 19F, 31P, etc. have a property called spin, and in this case spin half, which means that they produce a magnetic field that is similar to a bar magnet. When placed in an external magnetic field, these bar magnets can line up in one of the two ways, with or without against the magnetic field. These different orientation or states have slightly different energy levels. Electromagnetic radiations having energy corresponding to this difference in energy states can lead to the flip of the orientation of the lower energy state to the higher energy state. The size of this energy gap determines the frequency of the radiation required. Each element will have a different particular frequency. The frequency also depends on the magnetic field applied. However, the electrons themselves create a magnetic field which are around the nuclei, modify the applied magnetic field experienced by the nuclei, and therefore same type of nuclei in different chemical environment have slightly different energy gap and therefore give different NMR signals in the spectrum. So NMR spectra are a direct readout of the different chemical environment of the particular type of atoms present in the molecule. With this information, we should be able to determine the molecular structure of compounds. Having known the molecular formula through other structural means, we start the structural elucidation by measuring a simple 1D proton NMR spectrum. We use chemical shift, multiplicities, the coupling strength, and the integration to begin to understand the molecule. To determine the stereochemistry, it is important to do NOE experiments or nuclear overhauser effect experiments or NOSE experiments. This experiment gives proton correlation just like the COSY experiment but here the correlation is based on the transfer of the spin polarization using a cross-correlated relaxation and gives distance information between protons. You can use chiral derivatizing agent also to find the absolute stereochemistry. In summary, the NMR experiments are really important for the structure elucidation of organic molecules and also biomolecules. The BRUKER-NMR spectrometer situated in the Kariavattom campus of Kerala University is therefore critical for any chemistry laboratory. The equipment is equipped with a broadband probe, which means that you are able to record and measure spectra of any spin-active nuclei in the periodic table. The instrument is also capable of variable temperature measurements, that is, you can have temperature range from -150 to +150 degrees Celsius. The instrument is well equipped, therefore, to measure any 1D and 2D NMR experiments for structure elucidation. Thank you.
Hello everyone, I am Dr. Anidipti of the Department of Chemistry. You have already heard about the talk from Dr. Vinesh of ISER Trivandrum, who described to you about the various experiments that can be done in the 400 MHz NMR spectrometer at our CLIF, University of Kerala. Today, I will describe how we have used this instrument to characterize one of our compounds. As an example, I will take the compound which we had published in 2019. So this is a reaction where this particular compound called isatin reacts with an amino acid generating an isomethionylide, which adds to a dipolorophile to generate this type of spiropyrrolidine molecule. Going to the proton NMR, the proton NMR spectrum of this compound done in a 400 MHz instrument in our campus showed the different protons which are present in this molecule. As you can see, the peak at 11.2 is corresponding to the NH proton, and the peaks that you see here, that is the aromatic protons between 7 and 8. Then the 3 triplets, you can observe 3 triplets corresponding to the 3 protons, one near to the nitrogen and the other near to the thiophene ring. And the N-methyl proton was seen as a singlet at 2.15. The molecule was then subjected to 13C NMR analysis. So where we can find the spirocarbon at 76.2, the aromatic carbons in the usual 120 to 140 range, the cyanocarbons at 112 and 113 around that value, and also the methyl protons and the carbons in the pyrrolidine ring in a shielded region. In order to confirm whether which is the carbon which is containing 2 hydrogens, we have run a depth 135 NMR experiment. So in depth 135, we could observe one negative signal which indicated that we had only one carbon which corresponds to a CH2. All other carbons contained only one hydrogen, so therefore we get positive signals for all other carbons other than this carbon at 54, around 54. Having got all these one-dimensional data, we wanted to study the coupling of the protons present in this molecule. For this, first we have run a proton-proton COSY spectrum. From the proton-proton COSY spectrum, where on both axes you have the proton NMR, you can understand what is the coupling between the protons present in this molecule. To have a closer view, we have taken the expanded portion of this molecule spectrum, where you can see that the triplet centered at 5.12 correlates to the triplets of HA and HB at 3.59 and 3.79. So you can see 3 squares which is showing you the couplings. So the proton HC is actually coupling to both HA and HB, and HA and HB couples among each other also. So the proton-proton couplings can be well understood from this 2-dimensional COSY experiment. Now, in order to understand which carbon is connected to which hydrogen, we have run the HSQC spectrum. So, in this experiment, we have in one axis proton and the other axis carbon, and from the HS expanded portion of the HSQC spectrum, it is clear that the carbons at 112 and 113 ppm can be attributed to the cyanocarbons because they do not show correlation to any protons present in the molecule. So, that indicates that those carbons can be ascribed to the cyanocarbons. Also, we can understand that the triplets, that is the triplet at 5.12 is corresponding to the carbon at around delta 44.7 ppm, whereas the triplets at 3.59 and 3.79 delta is corresponding to the carbon 54.9. So, from that we understand that these two triplets are belonging to the hydrogens which is connected to the same carbon, whereas the carbon which is connected to this HC is coming at a delta 44.7 ppm. Now, in order to confirm the stereochemistry and the regiochemistry of this compound, a very important experiment called the HMBC experiment was conducted. So, here again on one axis we have proton and another axis we have carbon, but this gives the correlation even after one carbon apart. Like for example, here we can see that the carbons at 112 and 113, that is our cyanocarbons, is correlating to the proton HC at 5.12. So, that indicates that the cyano is actually closer to HC, but it is not close to HA or HB because there is no peak corresponding to that area, and that indicates the regiochemistry of our compound. Whereas the quaternary carbon at 76, that is the spirocarbon, is not correlating with the triplet at 5.12, but instead it is correlating to the triplets of HA and HB. So, that confirms the regiochemistry of this compound. So, in order to explain to you about one-dimensional NOE experiment, I have taken another molecule. So, here we are applying an RF signal to a single resonance in the spectrum so that the corresponding protons get saturated, that is the population difference between the high energy and low energy levels is forced to 0, that is the principle of NOE. And for example, in this molecule, suppose from the synthesis the stereochemistry at fifth position is already known, and then we have to confirm what is the stereochemistry in second position and third position. So, what we do is, first step, we saturate the protons at the C5 carbon. So, that enhance. So, from the 1D NOE spectrum, we will understand that the H2 signal gets enhanced by 3.6% and H6 signal gets enhanced by 4.8% and 2%. There are two protons in that carbon, but nothing happens to the protons at C10. And as a step 2, we saturate the proton at C2. The observation is that the H5 signal gets enhanced by 2.2% and H3 signal by 1.2%, whereas the protons at C10 gets enhanced by 3.6%. So, from this we can come to the inference that H2 is in the vicinity of H5. That means H2 and H5 are in the same direction, or its stereochemistry is alpha like that of H5. I already told you that the stereochemistry at H5 is known from the synthetic methodology. So, from these results, 1D NOE results, we can come to a partial structure for this molecule. This can be further completely confirmed by continuing the NOE experiment. If we take a third NOE, by saturating the proton at C3, we will see that the H2 signal gets enhanced by 2.9% and H10 signal gets enhanced by 2.9%, whereas nothing happens to the proton at C5. Final step of our NOE experiment, we saturate the protons at C10, that is the methyl protons, and we observe that the H3 signal gets enhanced by 7.9%, and this large enhancement suggests that H3 is beta like CH3. Thus, we come to the final structure of the compound where both the protons near to the methyl and near to the carboxylic acid are trans to each other. and thus NOE is a very powerful tool to understand the stereochemistry. So with this, I hope that you understood how to apply these NMR experiments for the structural elucidation of a small organic molecule. As a next part, Mr. Jibin, our NMR technician at CLIF, will explain to you how to run an NMR in our instrument and its software. Thank you.
Welcome to KU Padashala. My name is Jibin Raj, Technical Assistant in CLIF, University of Kerala, Kariavattom campus. Today we are going to discuss about NMR spectroscopy. All we know, NMR technique is a critical component in spectroscopy for the structural elucidation of organic compounds. Here we have BRUKER-400MHz solution state NMR, which consists tunable broadband probe, can detect nucleus such as H1, C13, N15, fluorine 19 and phosphorus 31. The working principle behind NMR comes from the spinning of nucleus and the very minute magnetic field generated by spinning nucleus. In the presence of an external applied magnetic field, the nucleus will align themselves either with or against the field of external magnet. When the sample is irradiated with a pulse of suitable radio frequency, energy transfer is possible in nucleus between the ground state to the excited state. This is called resonance. During the phenomenon, a corresponding electric signal detected by the receiver. The signals are Fourier transferred and recorded as NMR spectrum. We discuss about the NMR instrumentation. The NMR spectrometer mainly consists of a superconducting magnet having 9.4 Tesla field strength. The superconducting magnet is made up of niobium titanium metal alloy wire. Usually, superconducting wire has a resistance approximately equal to 0 when it is cooled to a temperature close to absolute 0 by immersing it in liquid helium. The magnet and the liquid helium reservoir are encased in a liquid nitrogen reservoir and in vacuum chamber to decrease the evaporation loss of more expensive liquid helium. We need 100 liter of liquid helium for 7 months and 50 liter of liquid nitrogen per week. The next is console. It contains the electronic hardware in which the principal units are IPSO, BSMS and VTU. IPSO, Intelligent Pulse Sequence Organizer, used to excite the sample and receive, amplify and digitize the NMR signal emitted by the sample. BSMS, Bruker Smart Magnet System, used to operate the lock and shim system as well as controlling the sample lift and spin. VTU, Variable Temperature Unit, vary the sample temperature in a controlled manner or maintain it in a constant value. The next one is probe unit. This is the probe box. Probe is the main part of NMR. It is the place where the sampled holder is placed. It contains an air turbine which helps to spin the sampled holder. The most essential component in the probe unit is the radio frequency transmitting and receiver coil. It is used to excite and detect the magnetization in radio frequency of sample. Next part is operator console. All aspects of the spectrometer operation are controlled from the operator console. It consists of a host computer, monitor, keyboard, etc. The design and implementation of experiment as well as the analysis of data are controlled by commands entered the operator console. This is the supporting equipment, air compressor and chiller. Air compressor will provide sufficient air for lifting and holding the sample in NMR spectrometer, and chiller will provide a dry constant air for lifting the sample. We can start the compressor and it will provide sufficient air towards the NMR spectrometer. We are going to sample preparation. Usually the sample is dissolved in deuterated solvents. We have the solvents deuterated chloroform, deuterated dimethyl sulfoxide, deuterated D2O and deuterated methanol. Now I am selecting the chloroform solvent made up of merc. Sample is dissolved in a vial using 0.5 ml chloroform, that is deuterated. Add the solvent into the vial and shake the solution using a vortex mixer. We get a clear homogeneous solution. Transfer the solution into NMR tube. This is the NMR tube using in CLIF. Transfer the solution into NMR tube. Now the sample is transferred into NMR tube. Insert the tube into the spinner and check the depth using a depth gauge. This is the depth gauge measuring scale. Now the sample is ready for NMR experiment. Now we can place the sample on the top of the NMR magnet. There is an air bud which will hold the sample for some time. After entering the command, the sample automatically goes to the probe. Now we can move to the software parts which are supporting our NMR spectroscopy. This is the main software used for NMR analysis. It's a Bruker Topspin 3.5 version. The main window. Here we can introduce the details of sample, type of sample analysis, different processing steps, and finally can publish the result. After entering the sample details, in Start tab we can move to Acquire. Here we can see different steps of analysis like introducing sample, log, tune, spin, shim, prosol, gain, and go for the result. After completing the whole steps, we can see the NMR analysis result. This whole steps can done automatically using another window called Automation window. Here the sample steps are automatically done by the system. Click the Add button. Here we can select the folder in which the analysis result could save. Here we can introduce the sample name. This is solvent selection. Here we can select the type of sample analysis like H1 or C13, etc. This is the selection for number of scans. After entering the required information, we can submit the analysis for good result. This is the H1 spectrum of ethyl benzene, in which you can see the peak positions or the chemical shift values are labeled at the top of the peaks and the number of protons are labeled below. If we closely observe the three peaks, the CH3 protons are labeled as A, which is a triplet, and B is CH2 proton, which is a quartet. The splitting depends on the number of neighboring protons plus one like manner, and the C represents the aromatic protons, which is a multiplet. This is the different type of chemical shift values corresponding for different type of protons. This is how we got a C13 NMR spectrum in which chemical shift values ranges from 0 to 230 pp. This is the chemical shift values for different type of carbon groups. This is the example of depth to 135 spectrum, in which we can observe CH and CH3 carbons in a phase opposite to that of CH2. 2D NMR also very helpful for the characterization of unknown compounds. This is the COSY spectrum which gives the hydrogen-hydrogen correlation. HMBC is another 2D experiment in which H1 chemical shift are plotted in x-axis and C30 values are plotted in y-axis. Each contour points representing the corresponding carbon and hydrogen which are correlated by multiple bonds. HSQC is another 2D experiment which gives the correlation of carbon and hydrogen which are directly correlated by bonds. If we look into the application side, NMR spectroscopy gives a wide variety of application in pharmaceutical, medical, organic and inorganic chemistry, food industry, and biochemical analysis studies, etc. etc.